In this video, we're going to find an expression or a formulation for our total potential energy stored in our two-dimensional triangular element, which is undergoing strain due to the application of external forces. Remember how we did this in one dimension. Our total potential energy is made up of the strain energy stored inside the system, which was this integral from 0 to L across the domain of our body, of all the stress and strain inside of our body. And in the derivation, we came up with this 1/2. We subtracted off of that the energy due to the fact that the external forces are not actually adding to the potential energy because those external forces are being used to create this strain energy. In this case, as far as a distributed load goes, there was really only one dimension where we could have a distributed force along the length of the body. So we ended up with a single integral that is an integral in one-dimensional space. After making substitutions of the approximations for our displacements and our stress and our strain, we came up with this form for the total potential energy stored inside a single one-dimensional element. What we're about to do is fairly similar, except that the total potential energy stored now in our two-dimensional triangular element will consist of the internal strain energy just like before, but there are now three separate components of external forces, because we could have external forces due to body forces, such as a density or gravity force, or perhaps some electrical property, which is causing every point inside my three-dimensional object to experience some force. Also, I can have forces applied along any surface of my two-dimensional or three-dimensional body. And of course, I can have forces applied at individual points. In that case, there'll always be forces applied at individual nodes. Similarly, our potential energy is made up of our strain energy. Our strain energy is still, just like it was in the one-dimensional case, 1/2 integrated over our domain, which is now a volume domain. And it is now stress and strain just like it is before, but notice that this is a dot product. So I could write this out as stress in the x direction times strain in the x direction plus strain in the y direction plus stress in the y direction plus strain in the y direction, and my shear strains and my shear stresses multiplied by each other. However, it'll be more useful for me to think in terms of this form because I already found approximations for stress and strain written as vectors. The three components of my potential energy due to external forces can now be written like this. The first term, my body force, which, since I don't want to write body, surface, and point out so many times, I'm just going to replace with the first letter. So my potential energy due to external body forces, I'm going to write as a triple integral. Remember, I'm integrating over the volume. Remember, psi is a vector that consists of my force, my displacement in both the x direction and the y direction, times, this is not a body force, even though I'm using F. This is actually a force per unit volume. It will become a force after I integrate over the volume. My forces applied along a surface, now this Fs is also not a force. It is a force per unit area, and it would depend on what surface an external force is applied. This is the same as it was in the one-dimensional case. Here, P is a vector of point forces applied at the nodes. It'll be a 6 by 1 representing the the force applied in the x direction and the y direction at each node. Now that I have this, and remembering that I can now make substitutions that for stress and strain, I can write out my total potential energy with the substituting in the approximations I made earlier. everything in this parentheses represents stress. So remember, stress is a 3 by 1. I have this as a as a row vector, so I'm going to have it as a 1 by 3. Notice here, I have my D matrix, which is a 3 by 3, multiplied by my B matrix, which is a 3 by 6, multiplied by my displacement vector, which is a 6 by 1. All the internal dimensions match. My external dimensions are a 3 by 1. That'll be a column vector. Here I have it as a row vector, so I'll need the transpose of that. These three matrices together will yield my 3 dimensions of stress. Likewise, everything in this parenthesis here, B times U, B matrix is a 3 by 6 multiplied by a 6 by 1. This will yield a 3 by 1. And remember, this represents my strain. Again, my body forces will be my shape matrix, which is a 2 by 6, multiplied by my displacement vector, is a 6 by 1. I want to get out of here. I'm going to need to multiply this or dot product this by this is my body forces applied at an individual point in the x direction and the y direction. So if I'm going to dot product this, I need a 1 by 2, so I need the transpose of that. For similar reasons, I need the transpose of the shape matrix times my u vector here multiplied by my forces applied along a surface. Note that I'm not giving you the dimensions of this term. The reason because this shape matrix is not the same shape matrix as it is here. It'll be a different shape matrix because this is along a surface. We'll discuss this matrix later. And of course, I still have external forces, point forces applied and multiplied by my shape function. I can do a little bit of rearranging, and I'd like to do that. I'm out of space, so I'm going to clear the board. I'm going to move this up to the top. Okay, so this is the same equation I had before. I can do a little bit of rearranging. So I can move my displacement vectors outside of my integrals. I'll have 1/2 my shape vector, my displacement vector as a row vector times this integral minus I'll have u times this integral plus this vector. At this point, before we move on to the next video, I'd like to point out a few things. One, after I do the integrations for these two terms, this will be a 6 by 1 vector. This will be a 6 by 1 vector. This is already a 6 by 1 vector. This represents body forces. This represents surface forces. This represents point forces. When I'm done, this will be a 6 by 1 vector, which will represent all of the forces applied on my body, at least all the forces applied on my body are equivalent forces at the 3 vertices or the 3 nodes. This integral from here to here is a volume integral consisting of 3 matrices. When I multiply these matrices out, I will get a single matrix. I will call my K matrix. This will end up being a 6 by 6. All right? So now that we have our expression for our total potential energy, in our next video, we will apply the principle of minimum potential energy to find our final form of our finite element method for a 2-dimensional triangular element.